The line integral is a super interesting topic from multivariable calculus. It's used a ton in physics, from work to Ampere's law to Faraday's law and so on. In this video, I'm going to give an introduction to the line integral, focusing mainly on visual intuition rather than notation and formulas. A scalar field is essentially a function that takes in multiple inputs and spits out one output. For example, let's look at the function f of x is equal to x squared plus y squared. This function takes in two inputs and gives one output. We can graph this function in the x, y, and z plane, which looks like this. Take a moment to look at certain points and the overall look of the graph. I encourage you to try a few 3D plotters and play around with it. Try functions you know in 2D with a mix of x and y. I've left a few in the description below. Before I talk about a line integral, I want to recap the concept of arc length from Calculus 2. Let's look at a continuous and differentiable function f of x. Let's take a step in the x direction, which I'll call delta x. Again, this is a finite number. Let's call the resulting change in the function delta y. I'm gonna call the hypotenuse of this triangle delta s. Take a moment to make sure you get everything before I move on. Now, delta s is the square root of delta x squared plus delta y squared. Essentially, to calculate the arc length, we need to sum up all these hypotenuses. So let's do that. Now that we have a sum, we want to make our changes as small as possible. So let's do that as n approaches infinity. This is the resulting sum. We can multiply and divide by delta t to get this sum. This is essentially an integral, which we can look like this. Now this integral is commonly abbreviated as the integral from a to b ds. So in this case, ds is equal to the square root of x derivative plus y derivative squared dt. Now let's talk about line integrals over a scalar field. Essentially, a line integral first deals with the curve C and a surface f. We can see the plot from the top. Notice how in this case, C is defined as a two-dimensional parametric equation, and we have f, which is a three-dimensional surface. The brighter spots represent bumps. So let's visualize this by rotating. This ends up laying our curve C on top of a 3D surface. The line integral is defined as summing up all the z values which C touches. Let's see what this means visually. We can project this orientation of f onto a 2D plane, and now simply it's a definite integral. Here we are summing up all the z values of f of x, y for all values in C. In notation form, it looks like this. Notice how we plug in the parametric equation into f and how ds expanded as we are going along a curve. I'm gonna play the animation once more for you to see again. Hopefully this picture also helps. Now I know a lot of people come here for help and also because they're interested in this topic. So I just want to quickly go over a textbook style problem quickly. So here's the problem. Evaluate the line integral of 3x squared minus 2y ds, where C is the line segment from 3, 6 to negative 1, 1. First, I'm going to graph C so we can get an idea of how it looks like. Next, let's parameterize the curve. It ends up being this from t is equal to 0 to 1. Now let's find dx by dt and dy by dt. Using our definition of ds, let's find ds. It happens to be the square root of 53 in this case. Using what we derived earlier, we can calculate this integral. Feel free to go back and recall this derivation. Now, evaluating this, we get 8 times the square root of 53. Now, let's talk about vector fields. A vector field associates every point in space with a vector, like this. I'm going to use color because the lines get too long. So this vector field is the function f is equal to x comma y. There are a lot of other cool looking vector fields like this one, or this one. Vector fields are used to describe a lot of things, like fluid flow, electric fields, magnetic fields, gravitational fields, etc. If you want to play around with vector fields, I've left a link in the website I created, which can visualize vector fields and also calculate divergence and curl. I'll talk about divergence and curl in a different video, so don't worry about it right now. Let's think about line integrals for vector fields. For this case, I have the vector field f that looks like this, and a curve c. R of t and c are the same function. To calculate the line integral of a vector field, we take the dot product of plugging the curve into the vector field function with the derivative of the curve. The graph in the bottom left is this dot product. The circle on the bottom right shows f of r of t and r prime of t. Remember, the dot product gives a value that says how perpendicular two vectors are from each other. Let's play the animation out. The graph on the bottom right shows the integral. You can see how it resembles an inverse tangent function, which this actually is. So to compute this integral, we take an integral from a to b of f of r dot r prime of t. There are a lot of things on the screen, so you should probably pause and let it sink in. I'm gonna play the animation once more for you to see. Like last time, let's quickly go over a textbook style problem. Here's the question. Evaluate the integral of f dot dr, where f of x comma y is y squared I hat plus 3x minus 6y j hat, and c is the line segment from 3,7 to 0,12. First, let's graph c. We can easily parameterize this line to look like this. Then, let's find f of r of t, which is equal to this, and the derivative of r, which is equal to this. Using the formula we had before, let's write out the integral. Evaluating it, we get negative 539.5. So there you have it. That's a quick introduction to the line integral. There's still a lot more to cover, like the fundamental theorem of line integrals, Green's theorem, so there might be a part 2. That's all. Thank you for watching.